So, good afternoon, students. This is your chemistry mentor, Dr. Umapati Reddy. So, in this video, we are going to discuss about the complex compounds, which is very important in JEE as well as in IIT advanced examinations. It is the most weighted chapter in JEE mains as well as in advanced. And look at this. This is our topic, complex compounds. So in this complex compounds, we are going to discuss this particular complex compounds is involving this type of introduction is the first, and terms which are present in the complex compounds in the next. After that, classification of elements, classification of ligands, not elements, sorry. And after that, we have various theories of coordination compounds. The theories of coordination compounds, the first is the Sedgwick-Lowry, that is the effective atomic number is the first one, and the second it is the Werner's theory, and the third it is the valence bond theory, and the fourth is the crystal field theory of coordination. So they are very, very important in the complex compounds. And after that, the important and very, very important topic, it is the isomerism is very, very important now. And followed by factors affecting stability of complex compounds. In the last, so what will be the importance of the complex compounds in our daily usage, in our daily life? So first of all, what are complex compounds? Before we go into discuss complex compounds, we have the addition compounds. So what are addition compounds? Addition compounds are what? So actually, when two are more than two, when two are more than two compounds, more than two simple salts solutions are allowed to chemically combined, then an addition compound is formed. When two or more than two simple salt solutions are allowed to chemically combined in a fixed ratio, then an addition compound is formed. So what is this addition compound now? Actually, suppose if you take the potassium chloride, you take potassium chloride aqueous solution plus magnesium chloride aqueous solution. This is also aqueous. When dissolved in water, you will get the aqueous solution. And 6 moles water, it is in a liquid. By adding these three components in a fixed ratio, you will get the KCl MgCl2 6 moles water. So this is an addition compound. The name of this compound is the carnallite. This is an addition compound. So when two or more than two simple salt solutions would mix here, one is the KCl and another is the magnesium chloride, and 6 moles liquid water fixed in a ratio, fixed ratio. By that you will getting what? KCl MgCl to 6 moles water. This is the carnallite. Again, we have one more. That is, for example, you take the potassium cyanide plus iron cyanide, ferrous cyanide. This is 4 moles KCN and 2 moles iron cyanide, ferrous cyanide. In a fixed ratio, you will getting the K4 FeCN6, K4 FeCN6, K4 FeCN6. So this is only only 4 moles of potassium cyanide and 1 mole of ferrous cyanide. You will getting the K4FeCN6. By taking potassium cyanide and iron cyanide in a fixed ratio, you will getting the potassium ferrocyanide. This is the potassium ferrocyanide. So both are the addition compounds. Both are termed as addition compounds because here this is the one simple salt, this is the another simple salt. Both were mixed in a fixed ratio. Finally, you will get the one compound which is called as what? Addition compound. In the previous case also, potassium chloride when mixed with magnesium chloride with liquid water in a fixed ratio, you will getting the carbonate KCl MgCl to 6 moles water. So both are the addition compounds. But here addition compounds further divided into two more types, two more type of compounds. Based on the nature of behavior in aqueous solutions. For example, when you take the cornolite KCl MgCl to 6 moles water, when dissolved in water, its behavior is different than K4FeCN6 when dissolved in water. So basing on the behavior of these compounds in aqueous solutions, these addition compounds further divide into two more types. One is the double salts and another is the complex salts. Again I repeat this, addition compounds further divided into two more types based on nature of behavior of these compounds in aqueous solutions. For example, let's see, cornolite when dissolved in water, it will dissolve in different manner when compared to the same type of addition compound potassium ferrocyanide when dissolved in water. Their behaviors are different. Cornolite behavior in aqueous is different, and potassium ferrocyanide behavior in aqueous solutions is also different. Therefore, addition compounds further divide into two more types. One is double salt and another is the complex salt. So now let us see in double salts. So what are double salts? Double salts are what? So double salts are also addition compounds, but their behavior is different in aqueous solutions when compared to the complex salts when dissolved in water. Their behavior is different and double salt behavior is also different now. So what are double salts? Double salts means simply by adding two simple salt solutions we will getting the same. Suppose potassium chloride, this is the aqueous solution, and magnesium chloride is the aqueous solution, and 6 moles liquid water, you will getting what now? KCl, MgCl2 and 6 moles water. So now this is the double salt. So when dissolved in water of this upon liquid water, this will be dissociates into K plus and Mg plus 2 and 3 Cl minus ions along with 6 moles liquid water. So this is happening with the double salts. Now we can define in this double salts. How can we define in this double salts now? And the other one it is what now? That is the other one it is what? That is the complex salt. Suppose you take the 4 moles of potassium cyanide aqueous solution plus Fe Cn taken twice. This is the ferrous cyanide. Now combine these two, you will getting the K4 FeCN6. This is a complex compound. Complex compound is this one, and this one is the double salt. But what will be the difference between them? So when dissolving this in water, liquid water, when dissolving in liquid water, complex compound is also undergoing hydrolysis, ionization. When dissolved in water, this complex compound is undergoing ionization. So here also double salt is when dissolved in water, it will also ionized. K plus Mg plus to 3Cl minus plus water. Now you will getting what here? 4K plus ions and FeCN6 minus 4. These are the two ions are obtained when a complex compound dissolved in water like that of K4 FeCN6. So what will be the difference between these? So double salt is undergoing 100% ionization when dissolved in water, whereas complex compound when dissolved in water is undergoing only partially. Therefore, we can defining a double salt. So what is double salt, sir? Double salt is defined as double salt. So it is defined as what now? The salts which undergo complete ionization and retains its identity in water. So this is called as what? The double salts. Why? How it retains its identity, I will explain now. And what about the complex salt? Now complex salt is complex compound. So salts which undergo partial ionization and lose their identity in aqueous solutions. Or termed as complex salts or complex compounds. So again I will repeat this, double salts which undergo complete ionization. So complete ionization means 100% ionization. So double salt generally undergoing 100% ionization and retains its identity in water. Whereas complex salts which undergo partial ionization and lose their identity in aqueous solutions. For example, in case of double salts, what will happen? So this is the double salt. When dissolved in water, you will getting all its constituent ions. So in double salts, we have what kind of ions now? K plus. Suppose if you take the independent or individual. So potassium chloride, generally if you have a potassium chloride now, so it will representing what now? For K plus ion and Cl minus ion. Whereas in case of magnesium chloride, it will representing Mg plus 2 and Cl minus. So independently it is having K plus Cl minus, it is having Mg plus 2 Cl minus. So for all these ions we have tests in semi-micro analysis. There are tests for all its constituent ions in simple salts. So when dissolved in water, again we will getting the same type of ions, K plus, Mg plus 2, Cl minus ions. Therefore, there are tests for all its constituent ions in case of double salts. So that is the different. Therefore, it will undergoing complete ionization. By that it retains its identity after water. After adding water, the same double salt is retaining its characteristics because it is having K plus, it is also having K plus, it is having Mg plus 2, it is having Mg plus 2, it is having Cl minus, it is also having Cl minus. But in case of complex salts, what will happen now? So when potassium cyanide, it is a simple salt, iron cyanide is a simple salt. So in this we have K plus ion, Cn minus. For K plus we have the separate test in the semi-micro analysis. In Cn minus also, for Cn minus also we have the separate test in semi-micro analysis. And Fe plus 2 also we have the separate test in semi-micro analysis. And Cn minus again the separate test in semi-micro analysis. By using semi-micro analysis we can identifying all the constituent ions in the simple salts. Whereas in case of after dissolving in water, what will happen? So we are getting only one K plus. For K plus only we have the separate test in the semi-micro analysis. But FeCN6 square bracket minus 4, this is the complex ion. For this there is no separate test in the semi-micro analysis. Therefore using semi-micro analysis we cannot determining the ion which is present after the dissolving of liquid, after dissolving complex compound in water. Only we are getting what na K plus and this complex ion. Complex ion further does not ionize. When dissolved in water, this is a complex ion, it does not ionized. Does not ionized. Therefore, before we have this test in the semi-micro analysis, after dissolving there is no test for the identification of complex ion, that is FeCN6 square bracket minus 4, and FeCN6 square bracket minus 4 upon liquid water, again it does not ionized. Therefore a complex ion does not ionized, or salts which undergo partial, this is a partial ionization when dissolved in liquid water, and lose their identity or not. Before we have this test for all its constituent ions, but after dissolving we never getting what na test for its constituent ions by semi-micro analysis. Therefore salts which undergo partial ionization and lose their identity in aqueous solutions, this is defined as what na, that is complex salt. Complex salt is defined as salts which undergo partial ionization and lose their identity in aqueous solution. So this is the major important difference between the complex compound and double salt. So let's what is a complex compound? So now what are complex compounds? What are complex compounds? So generally most of the transition elements can form most of the transition elements can form complex compounds, can form compounds most of the transition elements can form compounds with a fixed number of ligands. Most of the transition elements can form compounds with a fixed number of ligands in a specific arrangement by or through dative bonds. Most of the transition elements can form compounds with a fixed number of ligands in a specific arrangement via dative bonds. So this is what now? So such type of compounds are what? Complex compounds. So generally transition elements can form a large number of these complex compounds with a fixed number of ligands in a specific arrangement via dative bonds. Why this transition elements is going to forming large number of complex compounds? So it is due to what now? So why transition elements is going to exhibiting complex compound formation? So the reason behind this, why transition elements is forming complex compounds? The first reason it is due to small size. So how this small size is affecting complex formation easy? It is due to small size. So due to small size, what will happen? So due to small size, actually size is inversely proportional to Z by E. This is also called as what? Effect. This is the effective nuclear charge. So Z by E is what? This is effective nuclear charge. Effective nuclear charge. So smaller is the size, greater is the effective nuclear charge. Therefore, transition elements having small size means greater effective nuclear charge. Therefore, they can attract the lone pair electrons from the ligands very easy. That's why they can forming what? Complex compounds. Therefore, size is inversely proportional to Z by E, or size is inversely proportional to effective nuclear charge. If effective nuclear charge is more, they can attract the lone pair electrons from the ligands very easy. Therefore, complex compound formation making easy. Therefore, that is the second point now. And the third point, it is vacant orbitals. Vacant orbitals. So presence of vacant orbitals in the transition elements is making complex compound formation very easy. So due to these three reasons, transition elements is going to exhibiting complex compound formation very easy. So the first it is what? Now that is it is due to small size. It is due to small size, and size is inversely proportional to effective nuclear charge. So greater the effective nuclear charge, greater will be the attracting power of lone pair electrons from the ligands, making easy to forming of complex compound formation. And the third one, it is what? Now that is the vacant orbitals. Vacant orbitals in the central metal cation. So if vacant orbitals is absent, there is no choice to attract the electrons from the ligands into the metal. Therefore, vacant orbitals is also one of the important criteria to exhibiting this complex compound formation. Actually, so these complex compounds are very important in our daily life because the most familiar compounds like hemoglobin, so important complex compounds, important complex compounds, one is the hemoglobin. So hemoglobin, it is a complex of what? This is the complex of iron plus 2. And one also, that is chlorophyll. It is also very important complex compound, chlorophyll. So what is chlorophyll? It is a complex of magnesium plus 2. Chlorophyll is also belonging to our topic complex compound. Hemoglobin is also one of the important complex compound. Hemoglobin is a complex of iron plus 2, and chlorophyll is a complex of magnesium plus 2, and also one of the important that is the vitamin B12. Vitamin B12, so it is a complex of cobalt plus 3. So vitamin B12 is a complex of cobalt plus 3. So the another name of vitamin B12, it is the cyanocobalamin. You know this cyanocobalamin. And the fourth, it is cisplatin. So cisplatin is a anti-cancer drug. It is anti-cancer drug. It is a complex of platinum plus 2. So all these Fe plus 2, Mg plus 2, so not Mg plus 2, Fe plus 2, cobalt plus 3, platinum plus 2, all these are belonging to our transition elements. So most of the transition elements can form a large number of complex compounds. large number of compounds with a fixed number of ligands in a specific arrangement through D2 bonds. So such type of compounds are what now? That are complex compounds. So these are the most familiar examples of complex compounds. Hemoglobin is a complex of iron plus 2, chlorophyll is a complex of Mg plus 2, vitamin B12 it is a cyanocobalamin, a complex of cobalt plus 3, cisplatin it is an anti-cancer drug, it is a complex of platinum plus 2. So this is complex compounds. Now we are going to discuss the differences between complex compounds and double salts. So differences between double salt and complex compound. So what are double salts and what are complex compounds? So generally double salts is undergoing complete ionization, undergoes complete ionization, complete or 100% ionization, 100% ionization, and but these complex compounds undergoes partial ionization in liquid water. So undergoes complete or 100% ionization. The second it is the undergoes partial ionization. And the second point retains its identity in water. Retains its identity in water. Whereas complex compounds they cannot. They are losing identity in water. Complex compounds losing its identity in water. Losing identity in water. And the third point, examples, just now we KCl, MgCl2, 6 moles water, and potash alum, K2SO4, Al2SO4 taken twice, 24 moles water, and iron sulfate, ammonium sulfate, this is the Mohr salt, this is 6 moles water. So this is the Mohr's salt. So these are the double salts. This is the potash alum. This is what? This is we can call it as potash alum. So these are some examples for this double salts. Whereas in case of complex compounds, K4, FeCNC. This is the complex compound. Cu NH3 taken 4 plus 2 K3 FeCN6. So these are complex compounds. The most important is the when dissolved in water, these forming all its constituent ions. Therefore, number of ions increasing in this case of double salts now. So number of ions, number of particles increases when dissolved in water. When dissolved in water. Therefore, colligative properties increases in this case. So what is meant by colligative properties now? Properties which depends only on the number of solute particles. Properties which depends on the number of solute particles. So here number of solute particles when dissolved in water increasing. That's why colligative properties increases in case of double salts. Whereas in case of complex compounds, this is undergoing partial ionization. So compared to this double salt, number of ions less, number of particles decreasing when dissolved in water. When dissolved in water compared to double salts. That's why colligative properties. Therefore, colligative properties is less when compared to this double salt solutions. So here number of particles increasing, that's why molar conductivity also increasing. Molar conductivities of these solutions, molar conductivity is also increasing in case of this one, whereas in case of this one molar conductivity is decreasing. Molar conductivity is decreasing in case of complex compounds. And the sixth and very important point in this case of double salts now, so when dissolve double salts, they will forming all its constituent ions. Therefore, there are tests for all its constituent ions in the semi-micro analysis. There are tests. There are tests for all its constituent ions in semi-micro analysis. In semi-micro analysis, there are tests for all its constituent ions, because double salt when dissolved in water is going to forming all its constituent ions, whereas complex ion does not ionize. Therefore, for in case of K4 FeCN6, only for K plus is tests. For K plus only is there in the semi-micro analysis. For not the FeCN6 square bracket minus 4. Therefore, there are no tests for all its constituent ions in case of complex compounds. This is also very important. There are no tests for all its constituent ions in the semi-micro analysis. So these are the important differences between the double salts and complex compounds. So again I repeat this. Double salts undergoing 100% ionization or complete ionization, but this undergoes partial ionization. Whereas double salts retains its identity in water, whereas complex compounds losing its identity in water. But these are retains its identity in water. Example, this is the carnolite, this is the potash alum, KCl, MgCl to 6 moles water, this is the potash alum, K2SO4, Al2SO4 taken twice, 24 moles water, this is the FeSO4, ammonium sulfate, 6 moles water, this is the more salt. And these are the examples for complex compounds. K4 FeCl6, CuNO3 taken 4 square bracket plus 2, K3 FeCl6. These are the complex compounds. And in case of double salts, when dissolved in water, number of particles increases in the solution. Therefore, number of particles increases. Colligative property is directly proportional to number of particles. Therefore, colligative properties for this double salts, generally it is more compared to this complex compounds, because double salts when dissolved in water, they undergo partial ionization. Therefore, compared to these double salts, we are getting only less number of ions in the solution. Therefore, colligative properties are decreasing in case of complex compounds. And here number of particles increasing means conductivity is increasing, but here number of particles is decreasing, that's why molar conductivity is decreasing. And double salts is going to forming all its constituent ions. Therefore, there are tests for all its constituent ions in semi-micro analysis. Whereas in case of complex compounds, there are no tests for all its constituent ions in the semi-micro analysis, because complex ion does not ionize. Therefore, there are no tests for all its constituent ions in semi-micro analysis. So these are some important differences between the double salt and complex compound. Now let us discuss about the representation of complex compounds. Representation of complex compounds. How can we representing the complex compound? So this is the representation of complex compounds. So generally, suppose this is the metal, and metal is having generally the vacant orbital. This is the vacant orbital, and now this is the ligand. So ligand is having lone pair electrons. So this is the vacant orbital. This is the vacant orbital. This is the vacant orbital, and this is having a lone pair electron. So ligand must be containing lone pair, and metal must be containing vacant orbital. Therefore, they may combine together to form what? Na complex compound in the complex compound formation. So now you will getting what? Na one complex compound looking like M with this L. This is the one square bracket, and this is the X, and this is the Y, and this is the Z, and this is the plus or minus N. Now this is we can call it as what? Na complex compound. Now this is one complex compound representation. So what is here Y, and what is M, what is L, what is X, what is Z, what is plus or minus N? So this is the vacant orbital. So generally it is electron pair acceptor. This is electron pair acceptor because of this is vacant orbital, and it is ready to donate electrons into this vacant orbital. Therefore it is accepting. This is electron pair donor. This is electron pair donor. This generally electron pair donor we can say it as what? This is the nucleophile. Nucleophile, and therefore it is the electrophile. This is electrophile. So generally all electrophiles are Lewis acid. Electron pair acceptors are what? This is the Lewis acid. So it can acting as Lewis acid. Therefore this is the Lewis base. Electron pair. This is the ligand. It is donating electron density into the vacant orbitals of the central atom. Therefore it is electron pair donor. All electron pair donors we can say it as Lewis bases, and this is accepting electrons. Therefore this is the Lewis acid. Now here this is the before the square bracket we can representing it as what? This is the cationic sphere. This is cationic sphere. So after the square bracket, this is the anionic sphere. This is the sphere after the square bracket. The sphere where after the square bracket is represented by ionic sphere. Anionic sphere. This is the cationic sphere, and this cationic sphere, and also we can call it as what? This is counter cation. So Y is the counter cation. And this is the anionic sphere, and M is this is the metal atom, central metal atom. This is the metal atom, and L is the ligand. L is the ligand, and X is the coordination number. So X is nothing but what? Coordination number. And this is the anion, and this is the charge. So now here we have this total from here to here. So this square bracket region, this is the region, it is called as what now? This is the coordination sphere. Coordination, this is the coordination sphere. So the square bracket region, it is termed as coordination sphere. So before the square bracket, this is the cationic sphere. After the square bracket, we have the anionic sphere, and this is the cation, this is the anion. This cation is nothing but what? Counter cation. And this is the metal atom. This is the L is the ligand. X is the one number. That number is representing coordination number, and this is the charge which is present on the complex compound, and Z is the anion. So now we have various different forms. One is coordination sphere. So here the terms are what now? One is central metal cation. What is central metal cation? Central metal atom or ion. So what is meant by this central metal atom or ion? So this is the central metal atom or ion. And the second, it is a coordination sphere. What is meant by this coordination sphere? These are the important terms used in the complex compounds. And the third is the coordination number. Coordination number is the third important term which is used in our topic. And the fourth, it is very, very important, that is the ligand. So what are ligands and their classifications we are going to discuss in this video. So first is the central metal atom or ion. So what is meant by central metal atom or ion? So this is the central metal atom. So this is the central metal atom or ion. This is the cation which is bonded to some fixed number of ligands. The cation which is bonded to fixed number of ligands in the sphere. It is enclosing in the square bracket. It is nothing but what? That is the coordination sphere. So what is meant by central metal atom? This is the atom which is bonded to fixed number of ligands. The atom which is bonded to fixed number of ligands in the, this is what? This is square bracket. This is the coordination sphere. So what is meant by central metal atom? It is the atom. It is the atom. It is the atom which is bonded or attached to some fixed number of ligands by day 2 bonds. Day 2 bonds. So the atom which is bonded to some fixed number of ligands by day 2 bonds is nothing but what? That is the central metal atom or ion. So the atom which is bonded or attached to some fixed number of ligands through day 2 bonds is nothing but what? Central metal atom. This central metal atom must be containing vacant orbitals to form complex compounds. So that is the major criteria to forming a complex compound. So what is a coordination sphere? Coordination sphere, it is what now? This is the square bracket region. This is the sphere where metal is attaching with some fixed number of ligands. The sphere in which metal is bonded to some fixed number of ligands is nothing but what? A coordination sphere. Coordination sphere means the sphere in which the central atom M is bonded to some fixed number of L's. So such type of sphere is nothing but what? A coordination sphere. So again I will explain this coordination sphere. This is a sphere. In this sphere, the atom which is bonded to some fixed number of ligands via day 2 bonds or through day 2 bonds. So such type of sphere is nothing but what? Coordination sphere. And what is this coordination number? Coordination number, it is nothing but what? Number of chemical bonds between the M and L. Coordination number, it is a number. Coordination number is a number which representing the number of chemical bonds between the M and L. This is the M is the central atom, L is the ligands. So what is coordination number? Coordination number is the number, it is representing number of chemical bonds between the metal and all the donor atoms of the ligands. So that is nothing but what? A coordination number. And what about the ligand? So ligand, it is very, very important. So ligand, it is ligands. So these are very, very important in this complex compounds. So what are ligands? So the atom or ion or species which is having at least one lone pair, that is nothing but what? A ligand. So an atom or ion or species or molecule which is having at least one lone pair electron. So the species or atom or ion or molecule which is having at least one lone pair electron is acting as what are ligands. An atom or ion or molecule or species which is having at least one lone pair electron. So that is nothing but what are ligands. An atom or ion or molecule or species which is having at least one lone pair electron. So it should have compulsory one electron pair. So at that only it will be acting as a ligand. So this is nothing but what a ligand. So now we are going to discuss about the classification of ligands. So this is very important classification of ligands. So ligands are classified in many ways. Classified in many ways. So the first, the important classifications of ligands. So based on charge, ligands are classified into neutral ligands. So neutral means, for example, H2O is the neutral ligand. NH3 is the neutral ligand, PH3 is the neutral ligand, so etc. They are neutral ligands. Based on charge, one is neutral ligands, number two is positive ligands. So what are positive ligands? For example, H3O plus, this is the hydronium ion, is a positive ligand. NH4 plus, ammonium ion is a positive ligand, and NH3, NH2, this getting what a positive. So these are this is the hydrozonium, this is ammonium, this is H3O plus is the hydronium, and NO2 plus is the nitronium. So these are the, so based on charge, these are what now? Based on charge, ligands are divided into neutral ligands and positive ligands and negative ligands. So what are negative ligands? So negative ligands means, for example, negative in charge. So OH minus, F minus, Cl minus, Br minus, etc. These are the negative ligands. So classification of ligands classified into many ways. So ligands are classified in many ways. This is the first classification, that is the based on charge. So based on charge, ligands are classified into three different types: neutral ligands, positive ligands, negative ligands. Neutral, positive and negative ligands. And the next it is, second it is based on number of donor atoms. Based on number of donor atoms. So based on number of donor atoms, ligands are classified into monodentic. Second it is bidentic, tridentic, and the tetradentic, and the fifth it is pentadentic and hexadentate. So like that, hexadentic or hexadentate, hexadentate. So monodentate, bidentate, tridentate, tetradentate, pentadentate, hexadentate. So this is basing on the number of donor atoms. Suppose monodentate ligands, generally they can donating one electron pair. Whereas bidentate ligands can donate 2 electron pairs. Tridentate ligands can donate 3 lone pair electrons. Tetradentate ligands can donate 4 electron pairs. 4 electron. They have 4 donor sites. So based on the number of donor sites or number of donor atoms. If it have 5 donor atoms, therefore they can acting as what? Pentadentate. Hexadentate EDTA is a hexadentate ligand. They have 6 donor sites or 6 donor atoms. That's why based on number of donor atoms, monodentate, bidentate, tridentate, tetradentate, pentadentate, hexadentate, etc. And based on charge, neutral ligands, positive ligands, negative ligands, etc. And the third is and the third type of classification of ligands. Third type of classification based on the nature of bonding. Nature of bonding. So based on the nature of bonding between the metal and ligand, based on the nature of ligand, nature of bonding between the metal and ligand, there are one is flexidentate ligands. Flexidentate ligands, and second it is ambidentate ligands, ambidentate, and third one it is the chelate ligands, fourth it is the bridged ligands, and fifth it is the pi electron ligands, etc. So flexidentate, ambidentate, chelate, bridge ligands, pi electron ligands, etc. There are 5 different types of ligands based on the nature of bonding between the ligand. So based on the nature of bonding in the ligand, there are flexidentate ligands, ambidentate ligands, chelate ligands, bridge ligands, and pi electron ligands. So based on the nature of bonding between the metal and ligand, there are 5 different types. Based on the number of donor atoms, these are the different types. Based on the charge, they are neutral, positive, and negative ligands. So now let us discuss about the classification of ligands based on charge and number of donor atoms. Based on the charge and number of donor atoms. Classification of ligands based on number 1 and number 2. Number 1 is what now? Based on charge. Number 2 is the based on number of donor atoms. Based on charge is the 1, based on number of donor atoms is the 2. Classification of ligands based on number 1 and number 2. Number 1 is the based on charge, number 2 is the based on number of donor atoms. How ligands are classified into? So ligands classification. Ligands classification based on charge, based on charge and number of donor atoms. Number of donor atoms. So first, the first it is monodentate neutral ligands. Monodentate neutral ligands. Monodentate neutral ligands. So in the monodentate neutral ligands, first ligand and their name. So ligand and name of the ligand, and next is the donor atom and charge. So charge it is neutral, that's why charge is the neutral. So first it is monodentate neutral ligands. Monodentate neutral and monodentate. So what are the monodentate neutral ligands? For example, you take the H2O. H2O is the neutral ligand. H2O is the neutral ligand. This is the name of the ligand, it is aqua. And donor atom, in this case it is oxygen. And charge is the neutral. So neutral charge. And ammonia is also one of the important ligand. NH3 is also, this is the neutral and monodentate ligand. So on nitrogen we have the one donors, one electron pair, one lone pair electron, that can be the monodentate. Therefore this is amine. The name of this ligand is the amine, and donor atom is the nitrogen. And charge is again it is neutral. Charge is again it is neutral. And after this ammonia, this is the CH3NH2. This is the methylamine. The name of this one, it is methylamine. So it is also similar to what now, that is ammonia, amine or NH3. So this is the methylamine. In this case also nitrogen is the donor atom and the charge is again it is neutral. This is neutral in charge. So H2O, NH3 and this is the carbonyl. This is the C-double-bond-O. One is day-2 bond from oxygen to carbon and one lone pair on carbon. So this is 1, 2, 3, 4 and this is the 1, 2, 3, 4 and 5 and 6 is making a day-2 bond from oxygen to C. Therefore this is the carbonyl. So it is neutral in nature. This is the carbonyl, neutral in nature, and in this case carbon is the donor atom. Carbon is the donor atom and charge is again it is neutral in charge. So H2O, NH3, CH3, NH2, this is and again it is nitrosyl. Nitrosyl, this is the nitrosyl and nitrogen having the 5 valence electrons. This is 1 of nitrogen. These are the 2 are the oxygen. 2, 3, 4 and 5 and 6. So in this case, this is the nitrosyl. This nitrosyl, in this nitrosyl neutral ligand, nitrogen is the donor atom and charge is again it is neutral. And next it is dinitrogen. Suppose you take the nitrogen, dinitrogen, N triple bond N. So on nitrogen we have one lone pair and another nitrogen also we have the one electron pair. Therefore this is nothing but what now, this is dinitrogen. So in this also nitrogen is the donor atom and it is also neutral in nature. And dioxygen. So what is meant by dioxygen? O2 is the dioxygen. On oxygen we have 2 lone pairs and another oxygen we have also 2 lone pairs. This is called as what now? Dioxygen. This is dioxygen. So this dioxygen, in this donor atom is the oxygen. So oxygen can donate an electron pair to the central atom in the complex compound formation with the central atom. So it is also neutral in nature. So H2O, NH3, methylamine, carbonyl, nitrosyl, dinitrogen and this is the dioxygen. And next it is, so ligand, it is a ligand, name of the ligand, and donor atom, and then this is charge. So next it is pyridine. Pyridine. What is pyridine now? This is the pyridine. So this nitrogen is having one electron pair. The name of this ligand, it is the pyridine. So donor atom is the nitrogen in this case. So charge is again it is neutral in charge. Charge is again it is neutral in charge. This is the pyridine. So in pyridine, one of the, this nitrogen is having one lone pair electron that is able to donate an electron pair to the central atom. That's why that is monodentate neutral ligand. And then this is the PH3. This is the phosphine. So phosphine on the central atom. The central atom is the phosphorus, is having one lone pair. Therefore, the donor atom is here. What now? That is P, phosphorus. So it is also monodentate neutral, and it is it has charge is neutral in charge. And then PF3. This is the trifluorophosphine. So the central atom phosphorus is also having a lone pair. This is what now? This is trifluorophosphine. Trifluorophosphine. So here also donor atom is the phosphorus and it is also neutral in charge. And PPH3, trifluorophosphine, triphenylphosphine, this one. triphenylphosphine. In this also the central atom phosphorus is having a lone pair, therefore they can donate an electron pair to the central atom. That's why donor atom is the phosphorus, and it is also neutral in nature, neutral in charge. So these are the, what now these are the monodentate neutral, monodentate neutral. So these are the monodentate neutral ligands. Ligands what now? H2O, in that oxygen is the donor atom, in ammonia nitrogen is the donor atom, in methylamine nitrogen is the donor atom, in carbonyl carbon is the donor atom, in nitrosyl nitrogen is the donor atom, in nitrogen is the donor atom. This is the oxygen, dioxygen, oxygen is the donor atom. And next this is the pyridine. In the pyridine, this is the, what now? This is the nitrogen is having one lone pair, therefore that would be the donor atom. Nitrogen is the donor atom. In case of phosphorus, PH3, PF3, PPH3, in all these cases phosphorus is the donor atom, and all these ligands are neutral in charge. Therefore all they can donate an electron pair, only one electron pair. That's why they are monodentate ligands. Monodentate, what now that one? Neutral ligands, monodentate neutral ligands. Now the second, it is monodentate positive ligands, monodentate positive ligands, monodentate positive ligands. So what are monodentate positive ligands? So ligand is what now that one? That is positive ligand. Therefore ammonium NH4 plus, this is the ammonium ligand. So what now this one? This is ammonium ligand. Okay. So name of the ligand is the ammonium, and donor atom. So what is donor atom in the ammonium plus? And charge is the positive, because this is positive ligand, that's why charge will be the +1. So NH4 plus, this is the ammonium ligand. So the name of the ligand is the ammonium, and the donor atom is the nitrogen in that case, and charge is the positive. And then this is the hydrazine. This is the hydrazonium. NH3 plus is the hydrazonium. So in this also donor atom is this is the hydrazonium ion. So donor atom is the nitrogen, and charge is again it is positive. Hydrazine is the NH2 is the hydrazine. NH2 is the hydrazine. This is what now? It is similar to NH4 plus. So NH2 NH3 plus, this is the hydrazonium ion. And H2O is the water, but H3O plus is the hydrazonium. This is the hydronium. So hydronium ion is the H3O plus. So in this oxygen is the donor atom. This is the oxygen is the donor atom. In this what now that one? In this nitrogen is the donor atom. In this nitrogen is the donor atom, but having what now? Positive charge. Here oxygen is the donor atom. Therefore oxygen is the donor atom, and it is also what? Positive charge. So these are the some NO2 plus also there now. NO2 plus. This is the nitronium ion. Nitronium ion. So the nitronium ion, nitrogen is the donor atom, and also it is what now? Positive. And nitrozonium, NO plus. This is nitrosilium or nitrozonium. Nitrozonium ion. In this also nitrogen is the donor atom, and these are the important monodentate positive ligands. So all these ligands can donate an electron pair, only one single electron pair, therefore monodentate. And all these having what now? This is having positive, this is having positive, this is having positive, this is having positive, this is also having positive. In all these are the donor atoms. So in the first one, nitrogen is the donor atom. In this also, nitrogen is the donor atom. In this, oxygen is the donor atom. Oxygen can donate an electron pair to the central atom. In this also, nitrogen is the donor atom. In this also, nitrogen is the donor atom. Therefore, donor atoms are these donor atoms of these molecules or these species he is able to donate an electron pair to the central atom. By that there will be a formation of a day 2 bond between the central atom and ligand. So by that you will get in the complex compound formations. Next it is monodentate negative ligands. So these are very very important. Monodentate negative ligands. Monodentate negative ligands. I hope you are understand well my class. If you have any doubt, you please ask questions. The scroll number now. Okay, if you have any doubt, you call the scroll number.
On the screen.
Yes.